random processes, whichever we have not touched upon in the classroom. So what I want is I want you to make a note of this video lecture clearly, and we will discuss on some of the other things whichever you are not able to understand in this video lecture in the classrooms. Okay, so with that we will start. So in this video lecture, what we are going to understand is about Gaussian random processes, Poisson's random processes, and complex random processes. And also we will have a brief introduction about what is discrete time random processes. Okay, so for what we have done in the classes about the general random processes, we understood autocorrelation function, we understood power spectral density as a two different module, and in this particular video lecture we are going to understand about the special random processes that covers Gaussian, Poisson, and complex random processes. Okay, so now before first we will start with Gaussian random processes. So in Gaussian random processes, so you know what is the difference between random processes and the random variables. Okay, so random process is nothing but you will be having a sample function. Okay, so one or more sample functions, say x1 of t, x2 of t, which are all some, it may be discrete or it may be continuous. So accordingly, you know how to classify the random processes. Okay, so you are having so many sample function. Okay, and whenever you take, whenever you are concentrating only on one specific interval, only one time interval, say for example, t1, you will get one point from every sample. Okay, so if you organize all these one point from every sample, you call it as an x1, which is nothing but x of t1. Okay, so you get some set of values. This you call it as a random variables. Okay, so if you take in some another time point t2, you call it as an x2, which is another random variable. So what is a Gaussian random variable? So which is nothing but you are taking a sample values or you at a time t1, similarly sample values at time t2 or up to any definite amount of time, and you find every random variable whichever you have collected from the sample value itself is Gaussian. Okay, so please understand, every random variable should be a Gaussian. Then together we call this process as a Gaussian random processes. So you please clearly understand this definition. A random processes x of t is defined as Gaussian random processes if the sample function which we are taking at the time instant t1, we call it as a random variable x1. We take a time instant t2, we call it as a random variable x2. So similarly, till tk, we call it as a random variable xk, or jointly Gaussian random variable. So whatever random variables you are taking at different time instance, this should be Gaussian in nature for all values of k. K may be 1, 2, 3, 4 or anything. This should be Gaussian in nature, and for all the choice of t1, t2 till tk. Okay, so if you take only x1, x2, it should be jointly Gaussian. If you take consider x1 alone, it should be Gaussian. If you take x1, x3, it should be jointly Gaussian. So like so, this is the definition of the Gaussian random processes. Okay, so this particular definition applies for discrete time as well as for the continuous time random processes. So you can define it this definition either for discrete Gaussian random processes or also for continuous Gaussian random processes. Now whenever we are talking about Gaussian random processes, we are very much interested only in defining the probability density function. Okay, now here as we are talking about the joint Gaussian random variables. So let us define the joint Gaussian or joint probability density function. Okay, so we are taking this for k variables, random variables. All the random variables are Gaussian nature. So we define fx of x1, x2 up to xk of x1, x2 up to xk. This is defined as e power minus 1 by 2 x minus m the whole transpose into C inverse of x minus m divided by 2 pi the whole power k by 2 c power 1 by 2. So here what you need to understand is x is a random variable. Okay. M is nothing but a mean. It's nothing but a mean. And here it's a vector. Okay. So you can write it as a vector means. Okay. Vector of means. M is nothing but vector of means. So if you are having n random variable, you will be having n number of means. Okay. So mx of t mean for random variable tx1, mean for random variable x2, like this. We are having k number of random variable. So mean for all the k number of random variable is a matrix which is given by this. Okay. And similarly, the C is nothing but a covariance matrix. C is a covariance matrix. Okay. So if you know only the mean and the variance, okay, mean and the variance, you can define the complete density function of the Gaussian random variable. That is the speciality of the Gaussian random variable. So now how to write C? C can be written as Cx of T1 T1. Okay, Cx of T1 T2 like this till what? Till Cx of T1 Tk. This comes in the first row. Second row is Cx of T1 T2 T1. Cx of T2 T2 till what? Till Cx of T2 Tk. So this is the second row. Similarly, you will be writing K cross K matrix. So the kth row is nothing but Cx of Tk T1, Cx of Tk T2, like this, Cx of Tk Tk. This is the covariance matrix. Now you can see in this covariance matrix, you concentrate only on the diagonal. That is Cx of T1 T1, T2 T2, T3 T3 till Tk Tk. This diagonal of the covariance matrix is nothing but your variances. Other than the diagonal, whatever you are having here, say for example, second column, first row, Cx of T1 T2, similarly Cx of T2 T1, all these are the covariance. Okay, so you can remember accordingly. So diagonal is variances and non-diagonal is covariance. So please understand, you should only know the mean of the random variable, covariance of the random variable. If you know only these two things, you can define the Gaussian random variable. Okay, so therefore, absolutely, this special case give you an important property in the Gaussian. So please remember, we are talking about the stationary processes. What is stationary process? When do we say first order stationary? First order stationary is nothing but when the random variable, the mean of the random variable is a constant. We call it as a first order stationary. Similarly, when the random variable is second order stationary, we should be having mean as a constant and the auto correlation function should be defined only by the time difference, not on the absolute time. Okay, so the second order stationary is also called as wide sense stationary. Okay, so similarly, if you go for third order, fourth order stationary, you will be keep defining different properties. Okay, so in Gaussian random variable alone, you have a very unique property, that is nothing but a wide sense stationary Gaussian random process is also stationary in strict sense. So please remember, if we are talking about the ordinary random variable, we have to verify stationarity for every order. In the first order separately, second order, and second order stationary doesn't mean that it is stationary in the third order or fourth order. We have to verify for everything. Okay, so strict sense stationary in the sense it is stationary in all the order. So so we cannot just say that if it is wide sense stationary, it is also strict sense stationary for a normal random variable. But this is a very unique property, very important property and unique property in the Gaussian random processes. That is, when you find a random process is Gaussian and also y descent stationary, you can declare that it is also strict descent stationary. That means that any of the property does not vary with any of the order you are taking. Okay, so this is one unique property in Gaussian random processes. Okay, so please understand, if you know only the mean and the variances, you can just write the probability density function of the Gaussian random processes. Okay, so now let us do some problems so that you can easily understand. Say for example, a Gaussian random processes. This is the first problem. They have mentioned it is by instant stationary. Therefore, obviously we know the mean is a constant. So Ex is 4, and you can see the correlation is varying only with respect to time difference tau, not on the absolute time. So you can see Rxx of tau is given by 25 e power minus 3 modulus tau plus 16. Specify the joint density function for 3 random variables x of ti, I equal to 1, 2, 3, and ti equal to t naught plus I minus 1 by 2. T naught is constant. So you can you can do this problem. So let's say, what is the solution? First, you write down Rx of tau is given 25 e power minus 3 modulus tau plus 16. Okay, x bar is 4 is given. This is the general thing given. Now we have to define for 3 time instances. Okay, so whenever if they are asking you to find the density function, please remember you have to write only the mean and you have to write only the covariance matrix. So what is the size of the covariance matrix? They are asking for 3 time instances, right? 1, 2, and 3 time instances they are asking. So your covariance matrix will be 3 cross 3 matrix. Okay, so your covariance matrix will be 3 cross 3 matrix. Therefore, you what are the things you want to know? You want to know C of T1, T1. Okay, C of T1, T2, C of T1, T3, like this, C of T3, T3. So you want all these values. Okay, everything. So please remember what is the formula of covariance, a relationship between covariance and autocorrelation function. Covariance function Cxx of tau is nothing but Rxx of tau minus x bar the whole square. This is the relationship. Okay. So now first step what you need to define is you need to understand the time given. So what is what time instances they are asking? Time instance was mentioned as Ti equal to T naught plus I minus 1 divided by 2. They have given like this. So like, okay, they have given you like this. Now, this T naught is constant. Okay, so now what you do, as we know, autocorrelation function is only defined on time difference, not on the absolute time. What you do is, you take one more time instant Tk. Okay, see here we are given with Ti, which is a varying with I. Now you are defining a similar time instance Tk, which is nothing but T naught plus K minus 1 by 2. So instead of I, you are just replacing with K. Okay. Now what you need to do is you need to take the time difference only, not on the absolute time. So what is Tk minus Ti? Tk minus Ti is nothing but you have to separate both things. If you separate Ti from Tk, T naught and T naught will get cancelled and you are left out only with K minus I by 2. Okay, so K minus I by 2. You are left out only with this one. Okay, so now okay, you got T naught is K minus I divided by 2. Now what you need to do is you need to find Rxx of Tk minus Ti. So what is Rxx of tau given like this? Now you are going to write Rxx of Tk minus Ti. So will you write? It's nothing but in the place of tau, you have to write K minus I by 2. Okay. So 25 times of e power minus 3 modulus K minus I divided by 2. This is the time difference what you have got plus 16. Okay. So now here what you need to understand is, please understand, for modulus, since we are talking with modulus, 2 minus 3 and 3 minus 2 are one and the same. So here you have to substitute value of k equal to 1, 2, 3 and I equal to 1, 2, 3 because we are going to write a matrix of 3 cross 3 matrix. Okay. So k equal to 1, 2, 3 and I equal to 1, 2, 3. So please understand here you are having a modulus. Therefore, whether you are having k is 2, I is 1 is equal to k is 1 and I equal to 2 because whenever we take modulus of plus a equal to modulus of minus a. So remember that. Therefore, what we can do is we can write one by one as a step. So you are having Rxx of Tk minus Ti is given by this. So what is Cxx? What we want is only covariance. So what is Cxx of Tk comma Ti? Is nothing but Rxx of Tk comma Ti minus x bar the whole square. We have Rxx of Tk minus Ti is 25 times of e power minus k minus I. Okay. Factor 3 is there. So minus 3 by 2 k minus I divided by 2 plus 16. This is for Rxx. We have to subtract from mean. What is mean given in the question? In the question itself, they have given mean is 4. So minus 4 the whole square. So what will happen? This and this will get cancelled. You are left only with the first part. So what is Cxx of Tk comma Ti is nothing but 25 e power minus 3 by 2 modulus of k minus. Now what you can do, you can substitute for all values of k and all values of I. So k should be taking value 1, 2, 3. I should be taking value 1, 2, 3. Now let us understand when k equal to I. That is 3 combination. K is also 1, I is also 1, K is 2, I is 2, K is 3, I is 3. In all these 3 combinations, we have K minus I is 0. Therefore, we will have Xx of Tk comma Ti will be equal to 25. Am I correct? Okay. Next, when K minus I, difference is 1. Difference is 1 in the sense, it may be I is dominating or k is dominating. It may be 2 minus 3 or 3 minus 2. It may be 1 minus 2 or 1 minus 3. So what are the combinations that will work out? K equal to 1, I equal to 2, one combination, or I equal to 1, k equal to 2. Similarly, k equal to 2, I equal to 3, or I equal to 3, k equal to 2. In fourth of this combination, we will have k minus I, modulus of k minus I, or k minus I, difference is 1. So modulus of k minus I is equal to 1. Okay, so under this case, Cxx of Tx comma Ti is nothing but 25 e power minus 3 by 2. Okay, and the third combination is when k minus I, difference is 2. Difference is 2 in the sense, k can take value is 1, I is 3, or I can take value is 1, k equal to 3. This only these 2 combinations, I think. Okay, no other combination because we are limited with k is 1, 2, 3. I is also limited with 1, 2, and 3. So we have understood what will happen if everything equal. First combination, second combination is between these 2 things. Third combination is 1 and 3 and 3 and 1. Okay, so 1, 3 or 3, 1. This combination. So in this combination, k difference I is 2. So modulus of k minus I will be equal to 2. Okay, so therefore Cxx of Tk comma Ti is nothing but 25 e power minus 3 into 2 divided by 2. So into 3 into 2 divided by 2, we can write it as minus 6 by 2 directly, or you can write it as e power minus 3 only. Okay, so just for your don't get confused, it's only minus 6 by 2. So now how can you write the covariance matrix? How will you write the covariance matrix? So all the diagonals should occupy the variance, that is k is equal to I. Okay, so k equal to, so you can write k in the row 1, 2, 3, I in the column 1, 2, 3. So when k and I are same, k is 1, I is 1, k is 2, I is 2, k is 3, I is 3. we are having Cxx is 25. So you can write all the diagonals are 25. Okay. And then when k is 1, I is 2, or k is 2, I is 1. This combinations. Okay. So that is, you are going to now fill up this row. Sorry, this cell. You are going to fill up this cell. You are going to fill up this cell. You are going to fill up this cell. With what value? 25 e power minus 3 by 2. Okay, 25 e power minus 3 by 2. Here also you have 25 e power minus 3 by 2. Here also you have 25 e power minus 3 by 2. 25 e power minus 3 by 2. So what is this cell? This cell is nothing but, sorry, I think I made a mistake here. This is the cell 25. This is wrong. We have to fill here 25 e power minus 3 by 2 here, and not here again. This is 25 e power minus 3 by 2 here. So please understand, k is 1, I is 2, or k is 2, I is 1. That is, we are filling this cell and this cell. Similarly, 2 and 3. So 2, 3 or 3, 2. 2, 3 is this cell, 3, 2 is this cell. And finally, k equal to 1, I equal to 3. K is 1, I is 3. That is first row, third column. You are going to fill 25 e power minus 3 only. So this is 25 e power minus 3. Okay. Similarly, this is 25 e power minus 3. Okay, so please, you can write it down. Okay, so once you know the covariance matrix, that is more than enough. Okay, just by having the covariance matrix, and they have defined the mean is 4. So whichever, and also it is a stationary, right? So it is a strict stationary. So the mean is not going to change for x1, x2, x3 or any other cases. Okay, so mean is constant for, mean is the same for all the instances of time, and you are defining the variance of the covariances. Okay, now let us do the second problem in the similar procedure. You can see the second problem is zero mean Gaussian random processes as the autocorrelation function Rxx of tau equal to 6 e power minus modulus tau divided by 2. Determine the covariance matrix for the random variables x of t plus 1, x of t plus 2, and x of t plus 3. So what does it mean? It means that now we are going to write covariance matrix for totally of how many time instances x of t should also be included, t plus 1, t plus 2, and t plus 3. Okay, so these many instances you are going to write. Okay, so therefore totally your covariance matrix is of what size? 4 cross 4 matrix. Okay, 4 cross 4 matrix. So what are the things you want? Say you are writing in terms of k and I, right? So you want k 1, 2, 3, 4, I equal to 1, 2, 3, 4. Okay, so now what you have to do? They are not giving you any time instances over here. Okay, so instead you can say, you can take k minus I in the place of tau, you can define k minus I. Okay, so here you can write Rxx of tk comma ti is nothing but 6 e power. In the place of tau, you write k minus I modulus divided by 2. You write like this. Okay, now what is Cxx? Cxx of tk comma ti is equal to Rxx of tk comma ti. Why? Because minus 0. Because they have given you 0 mean Gaussian random variable. So you are going to substitute 0 here. So Cx and Rx are same. Okay. Now you can find what you can find. You want to write for the 4 time instances. So what are all the time difference you can take when k equal to I? When k equal to I, that is the case, both are 1, 1. Okay, both are 2, 2, 3, 3, 4, 4. These are all the instances k is equal to I. So what is the answer we are having when k equal to I? We have k minus I is 0. So 6 e power 0 equal to 6. So Cxx of tk comma ti equal to 6. What is the second case? K minus I difference is 1. When K minus I difference is 1. Difference is 1. So what are the instances? You can see here 1, 2 or 2, 3 or 3, 4. Okay, so it can be 1, 2 or 2, 1, 2, 3 or 3, 2, and similarly 3, 4 or 4, 3. So in the 6 instances, we will be having K is equal to K minus I, difference is 1. Okay, so on all these cases. So if the difference is 1, what is the answer? Cxx of t k comma ti is nothing but 6 e power minus 1 by 2. K difference I is 1, so 6 e power minus 1 by 2 if you substitute here. Okay. What is the third thing? Third thing is nothing but when K difference, okay, K minus I, difference is 2. How many instances the difference will be 2? K is 1, I is 3, or I is 3, K is 1. Okay, this is the first difference. Second difference is K is 2, I is 4, or I is 4, K is 2. Only this much. Okay. So under this case, Cxx of Tk comma Ti is nothing but 6 e power minus 2 by 2. So you will write it as minus 1. Okay. And find third thing, K minus I difference should be equal to 3. What are the instances? K is 1, I is 4, or K is 4, I is 1. Only these two instances we have. K minus I difference is 3. Okay. So under this case, what is Cxx of Tk comma Ti is nothing but you have to substitute 3 here. So you get 6 e power minus 3 by 2. So now you got the answer. You are ready to write the matrix, C matrix, Cxx of Tk comma Ti or tau. You can write anything which is, okay, write it as tau here. So it's a 4 cross 4 matrix. Already you know K is 1, 2, 3, 4. I is 1, 2, 3, 4. So when both are equal, we are having the answer is 6, right? So both are equal in the sense diagonal. So both are 1, 1, both are 2, 2, both are 3, 3, both are 4, 4. And when the difference is 1, it is 6 e power minus 1 by 2. So what are the cases? 1, 2, 2, 1, 2, 3, 3, 2, 3, 4, 4, 3. Okay, so let us write one by one. 6 e power minus 1 by 2. So here 1 and 2. Here this place 6 e power minus 1 by 2. 2 and 1. Second row, first column. 6 e power minus 1 by 2. Next you can see 2, 3. That is second row, third column. So this is second row, third column. This also 6 e power minus 1 by 2. Third row, second column, this one. Third row, second column is this one, 6 e power minus 1 by 2. And next is third row, fourth column, fourth row, third column. The same answer. Okay. So third row, fourth column is here. Fourth row, third column is here. So these are the places where K and I takes the difference of 1. Okay. So these are the places you are writing 6 e power minus 1 by 2. What is the third case? Difference is 2. How many places? 4 places only. First row, third column, third row, first column. The answer is should be 6 e power minus 1. So first row, third column, 6 e power minus 1. Third row, first column, here 6 e power minus 1. Similarly, second row, fourth column, fourth row, second column. Second row, fourth column, the answer should be 6 e power minus 1. Fourth row, second column, 6 e power minus 1. Finally, K and I difference is 3. We are having the covariance is given by 6 e power minus 3 by 2. So that is under first row, fourth column, fourth row, first column, only under 2 cell. So here 6 e power minus 3 by 2 and here it is 6 e power minus 3 by 2. Okay, so if the question is to define the density function of the Gaussian random processes, it is more than enough that you are only writing the covariance matrix and the mean. Okay, so generally the mean will be a constant and the covariance matrix is given here. Now let us do a similar problem, similar to the thing mentioned. So here you can see autocorrelation function is given by 13 times of 1 minus modulus of tau divided by 16 for tau ranging between minus 6 to plus 6, not more than that. And the mean is given as a zero mean Gaussian random variable. So whenever we have zero mean, we know covariance and autocorrelation are same. So for zero mean, okay, Cxx of Ti comma Tk or Tk comma Ta is equal to our Xx of Tk comma Ti. So you remember this one. It's for zero mean. So now what we want to find? We want to find the density function, that is covariance function for 5 time instances, I1, 2, 3, 4, 5. So therefore, please remember your C matrix will be 5 cross 5 matrix. So what are the values of K and I? K takes the value 1, 2, 3, 4, 5. I also takes the value 1, 2, 3, 4, 5. And they have defined the time instant. Similar to the first problem what we have seen, they have defined the time instant Ti equal to 2 times of I minus 1. So now you take 2 time instances, Ti equal to 2 times of I minus 1. You define another time instances Tk, which is equal to 2 times of K minus 1. Now from here, you take the time difference Ti minus Tk. So what is Ti minus Tk? It is 2 times of K minus I. It is 2 times of K minus I. Okay. So here, say I want to be more specific. So here instead of 16, you take it as 6, not 16. It is 6. Okay. So 2 times of K minus I. Now you write what is Rxx of Tk comma Ti. It's nothing but in the place of tau, you are going to replace with 2 times of K minus I. Okay. Which is nothing but 13 into 1 minus 2K minus I divided by 6. You have like this. Now this 2 and the 6 will get cancelled. So this becomes 3. So what is Cxx of Ti comma Tk? Cxx of Tk comma Ti is nothing but 13 times of 1 minus K minus I divided by 3. Okay, K minus I divided by 3. You have to take the modulus. I think here I forgot to write modulus. K minus I modulus. Modulus means that whenever you are in the negative side, also the same thing, you have to take it as a positive value. Okay. So K minus I, this is K minus I divided by 3. So you got the covariance formula. Now what is your job? You have to apply K equal to 1, 2, 3, 4, 5. I equal to 1, 2, 3, 4, 5. And then you have to find the matrix value. Okay. So now as usual, what we will do when K equal to I, okay, when K equal to I, this complete second part will become 0. Therefore, Cxx is equal to Tk comma Ti equal to 13. Okay. Now next, when K minus I, here it is I. Difference is 1. Difference is 1. What will happen? It can be in how many cases the difference is 1? You can see 1, 1. Okay. Sorry, 1, 2, 2, 3, 3, 4, 4, 5. These cases, vice versa and vice versa. It can be in other way also. In the sense, it can be 2, 1, 3, 2, 4, 3, 5, 4. Okay. So in all these cases. So you apply K minus I is 1 here. So what this becomes, this will become 1 minus 1 by 3. So 1 minus 1 by 3 is 2 by 3. So 13 times of 2 by 3. Okay. So when K equal to, under this case, you get Cxx of K comma Ti equal to 13 into 2 is, we can write 26 by 3. 13 times of 2 by 3, we can write it as 26 by 3. Okay. Next, when K minus I, a difference is 2. When K minus I difference is 2, what are the cases? You can see K is 1, I is 3, K is 2, I is 4, K is 3, I is 5 and vice versa. That is I can be 1, K can be 3, I can be 2, K can be 4, I can be 3, K can be 5. Okay, under these cases, K minus I modulus, the difference is 2. So this becomes 2 by 3. 1 minus 2 by 3 will give you 1 by 3. So Cxx of Tk comma Ti will become 13 by 3 under this case. Okay, 13 by 3. Now, next, when K minus I difference is 3. When K minus I difference is 3, what will happen? What are the cases K minus I difference is 3? 1 comma 4, 2 comma 5 and vice versa. 5 comma 2 and 4 comma 1. Okay, so K minus I difference is 3. 3 by 3 will get cancelled. So 1 minus 1 is 0. So Cxx will give you Tk comma Ti is 0. And next, when K minus I difference is 4. When K minus I difference is 4, 1 by 5 and 5 comma 1. Okay, these two cases. So this becomes what? 4 in the sense modulus of K minus I difference is 4. So what will happen? This becomes 4 by 3. If you put 4 by 3, 1 minus 4 by 3 will give you negative value. Please remember Rxx should not be negative value. Covariance should not be negative value. Therefore, this is invalid. This is invalid. And Cxx of Tk comma Ti equal to 0. So please remember, you are having the K minus I difference is 4. K minus I difference is 4. Here, if you substitute 13 times of 1 minus K minus I by 3, you can see it's a modulus. So 4 by 3, you will get 4 by 3 here. 1 minus 4 by 3 will give you a negative value. But covariance cannot be negative value. So you will not going to use this value at all. Invalid. So under the 2 cell in the matrix, you have to substitute 0. Okay, you are not going to substitute negative value. Please remember, you are going to substitute only 0. So now we got all the answers, I think. So now you can write them Cxx matrix, which is nothing but, okay, so you have derived all the values 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you can see when K equal to I, what is the answer? 13. We are having 13. So you can first of all fill the diagonal like this. Next, K equal to I, difference is 1, 26 by 3. So which are the points? 26 by 3, 26 by 3 here, 26 by 3 here. Then 2, 3 here, 26 by 3, 26 by 3. 3, 4, 26 by 3, 26 by 3, 4, 5, 26 by 3. Next, K difference I is 2, 13 by 3. So 13 by 3 here. Similarly, third row, first column is 13 by 3. Second row, fourth column is 13 by 3. Fourth row, second column is 13 by 3. Third row, fifth column is 13 by 3. Fifth row, third column is 13 by 3. And you can see when difference is 3 and any other difference, the answer is 0. So all the other left out cell, it should be filled with zeros. Okay, so this is how you are going to do the problems in Gaussian processes. Okay, now a very interesting thing is identically distributed Gaussian sequence. So identically distributed Gaussian sequence is a special case of the Gaussian processes. So here what we are going to have is, we are going to have like identically distributed, right? So you will be having only diagonal matrix over here. In covariance matrix, you will be having only diagonal matrix. Okay, so this is mostly a discrete time random processes. Okay, in which the mean and variances, mean is m and the variance is sigma square. Okay, the covariance matrix will be given by C x of Tk comma Ti will be given by, okay, sigma square I. This is what we call it as an identity matrix. In the sense, say for example, you want to fill 3 cross 3 matrix, then what you will write? Cxx of tk comma ti. You will write easily. You are going to find only one variance. So you fill the diagonal and all the other part will be 0. Okay, this is the identically distributed Gaussian sequences. Okay, so this is another interesting property of the Gaussian sequences. And one important property of the Gaussian process is nothing but when you have a linear time invariant system, it's a linear filter and your input to the linear filter is a Gaussian process. Okay, this side you are having an input. This side you are taking the output. You will find the output is also a Gaussian process. This is one property of the Gaussian random processes. Okay, so with that Gaussian random processes over, you can just go through some other extra problems from the book and you can complete it off. Next, we are going to understand the Poisson random processes. This again is an interesting. So if you want to understand what is how many people have entered today in any showrooms, okay, or in any theater, in some mall, you want to count how many number of the people. So you'll be usually having a counter. Okay, so this counter, what it will do, it will be just counting whenever any people are entering, it will be increasing the count. Okay, so this absolutely no, if you take at the 0th time, the counter will be 0. And after some 10 minutes, say for example, the counter will be having some value. After 20 minutes, the counter will be having some value either equal to what you have taken at the 10th minute or greater than that. Okay, so it is monotonically always an increasing process. Okay, because it is just only counting how many people are entering. It does not worry about how many people are exiting or how many people are existing inside the mall or how many people are going out of the mall. Okay, so this kind of processes we are going to model in terms of the Poisson distribution. Okay, this kind of process we will model using the Poisson distribution, and such processes we will call it as a Poisson random processes. Okay, so this Poisson random processes is an important example of a discrete random processes. You have not seen discrete random processes, but Poisson random processes is an example of discrete random processes. Okay, one example of discrete random processes. Okay, so here the main important thing is nothing but number of times an event occurs. Okay, and how many number of times an event had occurred is the main thing in Poisson random process, and it is a function of time also. Because we are talking about processes, right? So whenever you are talking about processes, it should be a continuous time function. And also it should be a number, okay, discrete number. So it is something similar to discrete random processes. Okay, so this event will occur at the random times. Please remember, we are talking about the event. This event will occur at a random time. Okay, now what you need to understand is if you are having x of t, this is going to count on number of event occurred or occurrences with time. This is the this is how a Poisson random process will be. How many events have occurred with respect to time. Okay, so this is always an integer value. Always a integer value and non-decreasing sample. Why do I say non-decreasing sample? Because please remember, we are having a counter which job is just to count how many people are entering. So if I am entering the mall in the 5th second, it will count to 1, and in the 6th second, if somebody is entering, it will count as 2, and again 3, 4. Like that, it will be ever increasing, and it is not at all going to decrease. So we call it as a non-decreasing sample. Okay, and so this one important thing about Poisson random processes is what we need to understand is two conditions are important. So what are the two conditions? Okay, first condition, you can make a note. First condition is in any vanishingly small amount of time, in a vanishingly small interval of time, in the sense, very, very small interval of time, only one event should have occurred. Okay, so that is the first condition. Event occurs only one in any vanishingly small interval. Any vanishingly small interval of time, only one event is occurring. This is the first condition. Second condition is this occurrence, no one event occurring. Say I am entering the mall, that should be completely independent of the any other person entering at any other time. Okay, so that is the second condition. Then only we can model it as a poisson. If I am entering and after 10 minutes my friend is entering, that is counted on me. Under that case, it is not a poisson random process. Okay, so please understand, in any vanishingly small interval of time, only one event is going to occur, only one people is going to enter, and two different times an event occurs should be completely independent of each other. Okay, so that is the second condition. Okay, so you write down the second condition. This occurrence time be statistically independent statistically independent. So what you need to understand is the number that occurs in any given interval is completely independent of the number that occurs in any other time interval. Okay, two time interval between 5 to 6 minutes, you are taking some number. Again, between 7 to 8 minutes, you are taking some number. You can see 5 to 6 is not overlapping time between 7 to 8. So you are taking two different time interval and you are counting the number. This number should be completely independent. Okay, so that are the two conditions. Okay, so now if you are defining, you have to understand what are the important parameters we are going to use in the Poisson random process. Is nothing but parameter lambda. Okay, so what is this lambda? Lambda is nothing but average rate of occurrences. This is the first parameter you need to understand. So this we have to define in any finite interval of time. Okay, so if it is a Poisson distribution, then lambda is the average rate of occurrences. Next is probability. That is probability that event occurred or not. Probability x of t equal to k. That is, you write down probability that exactly k occurrences happened over time interval 0, t. We can define it as a probability which is given by lambda t the whole power k into e power minus lambda t divided by k factorial. This k is nothing but occurrences. How many occurrences? It takes some integer value. Okay. Accordingly, you can define the probability density function for this Poisson process is nothing but fx of x is summation k equal to 0 to infinity. K is increasing. Okay. Lambda t the whole power k e power minus lambda t divided by k factorial into del of x minus k. So at every instant you have to uniquely define for the respective instances. Okay. Now interesting thing in Poisson distribution is mean and variance are equal. In Poisson distribution, mean equal to variance equal to lambda into t. Okay. And the mean squared value, if you find, you can directly find from this answer. Mean squared value is what? Mean squared value is nothing but variance plus mean the whole square. You can write like this, right? So lambda t plus lambda t the whole square. This is the mean squared value. So these are all some of the introduction to Poisson distribution, Poisson random processes. So now let us do some problems so that you can understand So you can carefully and listen to this problem. Aircraft arrive at an airport according to the Poissons. They have given it's according to the Poisson process at the rate of 12 per hour. Okay, so whenever we are talking about the rate, you please remember it's a parameter lambda is given. What is lambda? 12 per hour. They have given you 12 per hour. All aircraft are handled by one air traffic controller. If the controller takes 2-minute coffee break, what is the probability that he will miss one or more arriving aircraft? So what is the probability that he is going to miss at least one or more? So what they want from here is missing. What is the probability of miss? What is the time break he is taking? Finite time interval is 2-minute coffee break. So T equal to 2 minutes. Okay, probability of miss, we want probability of missing one or more aircraft. Okay, so one or more, na, we have to count from 1, 2, 3 up to infinity. That we cannot possible. So what we can do, we can just find probability of missing 0. Missing 0 since we are not at all missing anything. Okay, we can find this. Then what we can do is we can subtract this answer, whatever we are having, from 1 so that we get probability of missing one or more. So you can write like this. Probability of missing one or more is equal to 1 minus probability of not missing. Okay, probability of not missing. We are not at all missing anything. If you miss even one also, this counted here. So 1 minus probability of not missing. So here, not missing. We are having not missing. So k equal to 0. So what you are going to do, you are just going to use this formula. What is the formula? Probability of x of t equal to k lambda t the whole power k e power minus lambda t divided by k factorial. So probability formula, you can write it here, of x of t equal to k equal to lambda t the whole power k e power minus lambda t divided by k factorial. Okay. Now what is lambda? Lambda is 12 per hour given. T is 2 minutes given. Whenever you are substituting, you substitute such that lambda and t takes the same unit. So here it is given in hour, here it is given in minute. So you can either convert this to minute or this to hour or this to minute. So let us convert this to minute. So you can write like this. Okay, 12 by 60. You can write in terms of minutes. 1 hour will be having 60 minutes. So I am writing it as 12 by 60 and t equal to 2. Okay. And what? So probability of missing. Probability of missing is nothing but 1 minus probability of not missing, that is k equal to 0. That is 0 arrival. We are not at all missing. That is k equal to 0. So now you put k equal to 0 here. Lambda equal to 12 by 60. T equal to 2 in this formula. So what is probability of miss? Nothing but 1 minus lambda t the whole power 0. So this becomes 1. E power minus lambda t. E power minus lambda is what? 12 by 60 into 2 minutes. 12 by 60 into 2. 24 by 60 divided by k factorial. K is 0, right? So 0 factorial. 0 factorial is 1. So what is 24 by 16? You can substitute this later. You can write it as 1 minus e power minus 24 by 60. Okay, you can find this on the answer and you can write this later. You take the second problem. This is the second problem. Telephone calls are initiated through an exchange at the average rate of 75 per minute and are described by Poisson process. So 75 per minute. Okay, so lambda equal to 75 per minute. What is the question? Find the probability that more than 3 calls are initiated in any 5-second interval. So interval is 5 seconds is given. T is given as 5 seconds. So here again, what you need to do, you need to ensure that both the units are same. So 75 per minute is given. So you have to convert this into seconds. So you can write it as 75 by 60 seconds. Okay, so 5 seconds. Understood? So find the probability that more than 3 calls are initiated. So here again they have mentioned more than 3 calls. Exactly 3 calls, we can say k equal to 3. Okay, exactly 2 calls, we can say k equal to 2. But here they have mentioned more than 3 calls. So more than 3 calls means that k can take the value 4, 5, 6, 7, any value. So how can you do this? Probability that more than 3 calls is nothing but 1 minus probability of 0 calls minus probability of 1 call minus probability of 2 calls minus probability of 3 calls. You have to do like this. Okay, so now what is probability of 0 calls? Probability of 0 calls in the sense you are going to substitute k equal to 0. You already know lambda value and t value. So you can just write in the formula. What is the formula? Rewrite the formula here. Probability is nothing but lambda t the whole power k e power minus lambda t divided by k factorial. So when k is equal to 0, lambda t the whole power 0 becomes 1, k factorial becomes 1, e power minus lambda t only. So e power minus 70 by 60 into 5. Okay, 75 by 60 into 5. So this answer you can get it later. Okay. Now similarly you can do for probability of 1 call. Probability of 1 calls is nothing but k equal to 1. So what is you substitute k equal to 1. So 75 by 60. 75 into 5 by 60. The whole power 1 into e power minus 75 into 5 by 60 divided by 1 factorial. 1 factorial is obviously 1. Next, similar way you have to do for probability of 2 calls. Here now you put k equal to 2. So lambda t 75 into 5 by 60, the whole power 2, whole power k, right? So k is 2 into e power minus lambda t 75 into 5 by 60 divided by k factorial, that is 2 factorial. Okay, similarly, probability of 3 calls. Now k equal to 3. So 75 into 5 the whole power cube by 60 into e power minus 75 into 5 by 60 divided by 3 factorial. You can find e power minus 75 into 5 by 60 is common in all the factors. So you can get this answer individually. Then you have to, what you have to do, you have to find for probability of more than 3 calls. So I'm just leaving this to you. Probability of more than 3 calls is nothing but 1 minus whatever you got here minus here and minus here. Okay, so I'm just leaving this to you. You can complete. Now you can similar procedure. Let us find do the third problem. A small store has 2 checkout lanes that develop waiting lines if more than 2 customers arrive in any one time interval. Okay, 1 minute interval. So they have mentioned here. They have mentioned t is equal to 1 minute. Okay, they have mentioned t is equal to 1 minute already. Okay. Now, assume the Poisson process describes the number of customers that arrive for checkout. Okay, so how many number of customers are arriving for checkout is assumed. Find the probability of waiting line if the average rate of customer arrival is 2 per minute. So here they are giving 3 cases. First case is lambda is 2 per minute. Second case is lambda is 1 per minute. Third case is lambda is half per minute. Okay, so what is the question? Question is that find the probability of waiting line if the average rate of the customer arrival is 2 per minute. Okay, 1 per minute and 0 per minute. And here they have mentioned if more than 2 customers arrive. So more than 2 customers arrive in the sense when the waiting line is formed, probability we are going to find the waiting line. So when the waiting line is formed, if only we are having more number of customers per minute. Okay, so waiting line is nothing but probability that we are having more than 3 arrivals. Correct. Okay, so what you have to do now? You have to find 1 minus probability of waiting line. More than 2 customers only you are having waiting line. So when it is 3 arrival or more than 3 arrival, we will be having waiting line. Okay, so probability of waiting line is nothing but, again here, greater than or equal to 3, right? So you do probability of 1 minus probability of 0 arrive minus probability of 1 arrive minus probability of 2 arrive. So whenever you are putting 0 arrive, remember k equal to 0, 1 arrive, remember k equal to 1, 2 arrive, remember k equal to 2. So now case 1, let us take case 1. Case 1, what is lambda given? 2 per minute. So 2 per minute. And what is t given? T is 1 minute. So already both are in minute. So we need not do anything. So lambda is 2, t is 1. Okay, so what is the probability of waiting line in this case? 1 minus, you put k equal to 0. So 2 power 0 into e power minus 2 divided by 0 factorial. Okay, minus, you put k equal to 1. So 2 e power minus 2 divided by 1 factorial. Now you put k equal to 2 finally. So 2 power 2 e power minus 2 divided by 2 factorial. So I'm just leaving this to you also. You find this idea. This is for case 1. Similarly, you can do it for case 2. What is case 2? Case 2 lambda is different. So what is the lambda given? Lambda is 1 per minute is given here. So lambda is 1 per minute. T is 1 minute only. So both are in minutes. You need not do any kind of substitution. So probability of waiting line in this case 1 minus lambda into t is 1 into 1, 1 power 0, e power minus 1 divided by 0 factorial. Okay, I'm just substituting k equal to 0 first. Then I have to substitute k equal to 1. So 1 power 1, e power minus 1 divided by 1 factorial. Then I have to substitute k equal to 2, e power minus 2 divided by 2 factorial. So you can substitute this later. This is the answer when for the case 2. Similarly, you can do it for case 3. Case 3, lambda is what? Lambda is only half the person are arriving per minute. That is only one person arriving every 2 minutes. Okay, so that is 1 by 2 per minute. T equal to 1 minute. Both are in minutes again. So what is the probability of waiting line? 1 minus lambda t. Now the lambda t is 1 by 2. K is 0 for the first case, e power minus 1 by 2 divided by 0 factorial minus 1 by 2 the whole power 1, e power minus 1 by 2 divided by 1 factorial minus 1 by 2 the whole square, k is 2 here, e power 1 minus 1 by 2 divided by 2 factorial, k is 2 here. See, what I am doing is I am just simply substituting in the formula. The only thing what you need to understand distribution is what is how to identify lambda, how to identify t. T is nothing but the time interval given. Lambda is nothing but the rate of occurrences, and k is nothing but how many exact occurrences. Okay, so if you know how to find these 3 parameters, you are just substituting in the equation of probability given. So this is the equation of the probability to get the answer. Okay, so that there is nothing more than this in Poisson's distribution also. So complex random processes and discrete random processes I will be covering in the next video. Okay, thank you.